This is an example on a uniform motion with a constant velocity. Here, the runner moves along a straight line at a constant rate towards point B, and this point B is located 20 meters away from the starting point A. It took him 4 seconds to reach point B. What is the runner velocity? It took the runner 10 seconds from the starting point to reach his destination. As he passes through point B, what is the distance from the starting point of this diagram explains part B of the problem, where it shows that the runner is moving with a constant velocity from A until it reached its destination here at this width, and at a time of 10 seconds. So it is required now to find x final, which is the distance from the starting point up to the destination point. Since the runner runs at a constant rate, so its velocity is constant. So in this case, the average velocity is the same as the instantaneous velocity. So the initial position of the runner is 0, it starts at the origin, and the initial time also will be set equal to 0. In this case, we just substitute the total distance, which is 20, and that is divided by the elapsed time. We'll get 5 meters per second. And obviously the direction of the particle is clearly indicated in the figure, where it moves due east. As the runner starts from the origin with a constant speed until it reaches the final destination, which is a distance x final from the origin, it reached there with a time of 10 seconds. So in this case, the problem is simplified. As long as the velocity is constant, this means that the average velocity is the same as the instantaneous velocity. And we can apply the formula of the average velocity, which says delta x over delta t, or delta x equal vx multiplied by t, where t initial is considered as 0. By substituting the values in this equation, you will get the total distance from the starting point as 50 meters, and it's directed towards the x-axis. In the coming slides, it's interesting to watch a demonstration about the constant velocity in an experiment.
We'll float this glider on a cushion of air to reduce the friction which normally slows down moving objects. After the glider is pushed, it moves smoothly down the track until it hits the bumper at the end. These dots will track the motion of the glider every half second to record the glider's position versus time. What does the spacing of the dots tell us about the glider's velocity? Since the spacing between dots is constant, the velocity of the glider must be constant. What happens to the velocity when the glider strikes the end of the track? As this vector representation shows, when the glider strikes the end, the velocity is reversed in direction, but the magnitude or speed is the same. Here is the glider moving at a higher velocity,